Okay, so I want us to discuss this tutorial, right? As you can see, it's tutorial number 1. So, based on this tutorial, we are given that we should determine the given set together with the specified operations of addition and also the scalar multiplication if it's a vector, right? Then let's say if it is not, list all the engrams that fail to hold. So, now checking the first one, we're given that they say that for the first one, they say that V is equals to x y xy element of r squared such that xy is greater or equals to 0. So for us to be able to solve such a question, what we are going to do, right, we are going to say that, let me do this. I'm going to say, remember that the question says that V is equals to xy, which this is an element of r squared, such that xy is greater or equals to 0, right? So for us to solve this, we're going to come and say that first I need to check closure, all right? First I need to check closure under addition. So for me to check closure under addition, I'm going to come and say that I need to let two vectors. So I can let V and U be an element of V. You see, right now I can let U and V be an element of V. So when I let this, it's going to be such that V is equals to x, let's say x1, y1, which this is an element of r squared. You see, right, such that x1, y1 is greater or equals to 0, and I let u be equals to x2, y2, which this is also an element of r squared, such that x2, y2 is greater or equals to 0, right? Then for me to check closure, I'm going to add these two. I'm going to add v and u, and this is going to give us x1, y1 plus x2, y2. Now if we check this, we're told that we're going to use the usual addition and multiplication and scalar multiplication, right? So we're going to come here and say this. We're going to say this is x1 plus x2, y1 plus y2. So now, since we know that this is also an element of r squared, according to that definition, we have only proved partial. You see right now? So it means that we must also prove this part. So to check now, it means that for this to be true, we must have a case that x1 plus x2 times y1 plus y2 to be greater or equal to 0, right? So we want to ask ourselves, is this true? So initially someone would say that I can find this, right? Someone would say that I can find this. So let's see that. Someone would say, or let's say this, someone would say that if I could multiply this through, I would get x1, y1 plus x1, y2 plus x2, y1 plus x2, y2 if I cross multiply them. And we know that initially we know that x1 and x1, y1, which is this one, is equals to 0. X2, y2, which is this one, is equals to 0. What about these ones? Someone would say that I could come here and say that x1 is greater or equals to 0 over y1, which this is greater or equals to 0. You see right now? So someone would say that if I come and plug that here, this would be 0 plus x1, y2 plus x2, y1. So I'm trying to show all possibilities, right? And then Now we try to find this one. We know that x1 would be this, and we know that x2 would be 0 over y2, which is right. Then we know that since x1 and x2, we know that they are also we know that this would be right. But what if, remember, what if y1 is 0? What if y2 is 0? So this won't be true. You see, right? This won't be true for y1 and y2 not equals to 0. You see, right? So for us to come up with a clean way to show this, we can use a counter example. For us to come with a clean way to show this, we can come up with a counter example. Because you have seen here, what if y1 is 0? What if y2 is 0? So that is not going to give us a 0. It's going to give us undefined. So it means that we're going to say by counter example, we're going to come to counter example and say by counter example, we're told that first I should let v. It says that when I take these two elements in v, says when I take these two elements, let's say I take -1, -2. When I multiply these elements and -2, I must get greater or equal to 0, which this is true. You agree, right now? And again, so I'm going to take this, and if I let u, we know that if I let u, let's say I let this one can be 2, this one can be 0. You see, right? Or it can be 1. It's up to us. As long as when I multiply these two, 2 and 1, I'm going to get greater or equal to 0, which is true. And this is an element of v. This is also an element of v. So, and this is an element of r squared. This is also an element of r squared. So, now if I say v plus u, I'm going to get -1 -2 plus 2, 1, which this will be -1 plus 2. Do I have, let me see, do I need that? It's fine, matter. So here I will have -2 plus 1, and this will be 1, this will be -1. But if we check 1 and -1, this is going to be less than 0. You see, right? And in which this will imply that v plus u cannot be an element of v because it didn't satisfy that condition. You see, right? So we have shown this by counter example. Then we can say, therefore, closure under addition does not hold. Since they said we should show all that do not hold, after checking closure under addition, we can also check closure under scalar multiplication, SM, right? So you see that if I come here and let alpha be an element of R, and I let V to be equal to xy, which we know that if I take xy to be greater or equal to 0, and this is an element of R squared, right? And this will be an element of V. So if I take this, right, then I now check scalar multiplication. This will be xy, which this will be alpha x, alpha y. Then we check this. This we know that it's an element of R squared. Then we check this, right? Want to check, this is an element of R squared, but is this greater or equal to 0? Let's check that. So this will be equal to alpha squared xy. And this was defined to be greater or equal to 0. And this one, we know that it will always be positive. So this will be greater or equal to 0. You see right now, this will always be greater or equal to 0. So this one holds. So scalar multiplication does hold But then this one, scalar addition does not hold, so there's no need for us to check those properties. You see, right? Then we can just stop here for this question. So now after that one, we can check B. B, we're given that V is equal to ABCD such that AD is equal to 0, right? With usual addition and scalar multiplication. So for that one also we can come and say the question says V is equal to AB CD such that AD is equal to 0. We see, right? They say with usual addition and scalar multiplication. So for us to prove this, we are going to come and say that for us to prove closure under addition, we're going to say that we're going to let V U to be an element of V such that V will be equal to A1, B1, C1, D1 such that A1 times D1 is equal to 0. You see that, and this we know that it's an element of V. And we let U to be equal to, we know that we're going to have A2, B2 this one, C2, D2 such that A2 and D2 is equal to 0. And this is an element of V. We see, right? So when we come and add these two, we are going to have A1, B1, C1, D1 plus A2, B2, C2, D2. And this will give us what? This will give us A1 plus A2, B1 plus B2, C1 plus C2, D1 plus D2. And this is an element of R squared. We see right now, even though not R squared, man, this is an element of M2R squared. No, M2R. Yeah, I'm just gonna put it like this. This is an element of M2R, right? So now, even here, just that they didn't say that this is an element of M2R or M2 by 2R, right? If they wanted, they would have said it, but then they didn't say it, so it means that there's no need for us to check that. But we see that indeed this is an element of M2R, so it's not important to say that since they didn't say it, right? So now the condition that we should check is that if I take A1 plus A2 and multiplied with D1 plus D2, am I going to get 0? That is the question that we're asking. You said right now, am I going to get 0? So we could do many things to do that. Some they would say that let's check it like this. Let's say that we have A1 plus A2 and B1 plus B2. Let me do this again. So some would say that I would take the determinant of this A1 plus A2, B1 plus B2, C1 plus C2, D1 plus D2. And I say that the determinant of this is equal to minus C1 plus C2 times B1 plus B2, right? Then this simply means that these two multiplied are giving us 0. You see right now. But the question is, how are you going to find the values of this? You said that someone could think of it like this, then they do the determinant of this just to show that this is 0. You see, right? But then the problem is, after showing that this is 0, after showing that A1 plus A2, that would imply that this is equal to 0. It means that we would have to multiply A1 D1, you see that it would lead us back to what we had at that time. A2 D1 plus A2 D2. You see, right? Then going back, we know that A2 D2 A1 D1 are 0. We know that this is 0. This is not that one. We know that this is 0. So this would imply that this is 0 plus A1 D2 plus A2 D1 plus 0. You see, right now, since we know that those ones are 0. But the question is, how do we find A1, A2, D2, D1? Obviously, you would come here and say that for me to find A1, I'm going to have 0 over D1, and this will be 0. But what if D1 is 0? You see that even if we can try this approach, it could be a problem. What if D1 is 0? You see, so it means that this approach would not work. Right, this one would not work. So we need to use a counter example to disprove this. You see that we were able to find a counter example, but we must come with some examples to say that if, let me say I let this because of this, and then I try to do it and see if it's going to give me those things. So according to matrices, having such a counter example is a bit simple, because we're going to say this. Let me erase this. We're going to say that if I'm going to use a counter example, let me come and say by counter example. By counter example. If I come and say by counter example, I'm going to let V to be equal to, this should be, if I want to have this two multiplied and I get 0, that's the only way. One of them should be a 0, you see, right? And then let's say this is 1, 1. And then this will happen such that we know that 1 times 0 will give us 0. You see, right? This will be an element of V. So again, if we take U to be, let's say now this one is 0, this is not 0, such that 0 times 1 is equal to 0, which this is an element of V. We see, right? But when I add them, when I add V plus U, I'm going to get 1, 1, 1, 0 plus 0, 1, 1, 1. So these ones, these two, you can put in number. Also, this constant, you can put any number. Just use 1, 1 for simplicity, right? But we only care about these ones. As long as these ones, when you multiply, they give us 0. The rest, you can choose anything. Then this will be 1 plus 1. So I can use 1 plus 0, 1 plus 1, 1 plus 1, 0 plus 1. And this will be 1, 2, 2, 1. But when I multiply this, see, right, 1 times 1 is not 0. Hence, this condition does not hold. You see, right, and this condition won't hold. It means that we must come and say that if I have this, we must come and say that V plus U is not an element of V. You see, right now. Hence, V is not a vector space. You see, since this condition does not hold. So now, if you want also, you can check scalar multiplication. So I'm going to leave that work to you to check the scalar multiplication to what do you get when you use a scalar multiplication. Then also, you can try to do the same thing. Check C, use a condition where X, Y, Z, when you multiply them, you're not going to get 0. Then you check D, you check E, you check F, you check G. And then we can see what we do about it afterwards.